So I'm going to talk about Apache Spark and why I think that it makes a really powerful platform for building distributed machine learning systems. I'm going to just about me. So I'm a long-time user of Spark. I organized the London Spark meetup, by the way, so if anyone finds this interesting, then do come to the meetup. And as Ian said, I run the data science team at Skimlinks. So Skimlinks, we are, let's just say we're an ad tech company. We mainly deal with very large quantities of text data, websites. We analyze lots of it. We analyze around something like 1 billion very small documents a day. And so we're using Spark to build systems that can analyze that text. And in the main, you can think of it as things like classifying text according to what topic that piece of text is about. OK, so really over the last year, interest in Spark has gone a bit crazy. And it's for things like this. This is the Daytona Gray Sort benchmark from last year, where the team from Databricks won the competition. And they sorted 100 terabytes of data in 23 minutes using 200 machines. The previous record was a Hadoop implementation at 72 minutes with 2,000 machines. So everyone's excited. It looks interesting, and I think that a lot of this bars is quite justified. So I'm just going to go through some really basic concepts that you need to understand and know what Spark does. I'll go through this quite quickly. Who's actually used Spark before? OK, so I won't spend loads of time on this, but I'll just bring everyone up to speed. So this is a central concept. It's the RDD. It's a resilient distributed data set, I think. But really, this is just a way of distributing a massive data set, a large number of rows of data across a cluster of machines. And so you can see this kind of rectangle, and then these blue things are supposed to represent what are known as partitions, and you can sort of think of them as files. And then this will be distributed over the whole cluster. But that's invisible to you, really. All you know is that it's a large number of partitions or files distributed across your cluster, but you don't know which thing is on which machine. This is some Spark code, some PySpark code. This first, this laser pointer didn't work. No, it doesn't matter. So this first line is just a way of, I've just made an artificial RDD in this case. I've just taken 12 numbers and distributed them across the cluster. Obviously, you would only do this if you had more than 12 numbers, but just for this example, I've made 12 numbers, and I've distributed them into 4 partitions. Those were those blue things that I showed you on the last slide. And then, after I distribute it, I just bring it back to the master node, and this is just a normal Python list now. It's just 12 numbers. So what can you do with these RDDs? So this is another key. This is a key function, map. Everything fits into the MapReduce framework that you're probably familiar with already. And here I'm just running a map with a function, a lambda function, that takes the modulus of a number. It takes it's the modulus 3 of the number. So with this list, it applies this function to every single element of this list, and it gives me this result, as you would expect. And it's completely element-wise at this stage. So this map is as an element-wise operation. It applies to each element separately. So that's what this indicates. Like all of these partitions can be processed completely separately and independently across the cluster now. So it's nice and clean. So now I'm zipping these two lists together. This is normal. This is similar to the Python zip built-in. The first elements are 0, 1, 2, 0, 1, 2, 0, 1, 2, and then the other elements are 0 to 12, 0 to 11. So I've just paired up those two lists, and now I collect them onto the master node so you can see them. And then I'm introducing this other really important function, which is reduce by key. And this is a bit like reduce in Hadoop, if you're familiar with that paradigm. I'm just going to apply this reduction. I'm going to reduce using this function for all of the elements which are associated with each of the keys. So there are 3 distinct keys here, 0, 1, and 2. And you can see, like, if we just go through the first one there, The first pair is 0, 18. If you look here, you can see 0. Oh, this laser pointer is not working. 0. I've got the 0 keys are 0. The values for the 0 key are 0, 3, 6, 9. 0, 3, 6, and 9, and that adds up to 18. And the same thing for 1 and 26. And really, once you understand those two things, you can do nearly everything that you need to in Spark. It's just map reduce. But something key that you need to understand is that when you do this reduce by key thing, for instance, the 0 keys may be on any partition, and they may be on any machine. So you have to you have to do what's called a shuffle, and the data will have to go between machines, which is what this kind of these arrows are supposed to indicate. That there's a lot of inter-machine communication happening, and in the main, this is something to be avoided when you can, because it takes a lot of I/O network traffic, and you may see some suffering in performance if you do lots of shuffling on very, very large data sets. And by large, just to give you some sense, we are looking at around 30 terabytes of data on 40-node clusters. That's what we think of as a large, like over 10 or 20 terabytes of data is a lot of data for Spark to deal with, and you need to start thinking about how to, design your system so that they work well with so much data. When you start using Spark on large data sets, that will definitely crash a lot. And here are some kind of rules of thumb that are well worth thinking about. So make sure you set the number of reducers sensibly, and I'll talk about that in a bit more detail later. Configure the Spark cluster properly, I'll talk about that too. Don't shuffle, I've mentioned. Don't group by. I won't go into details there, but you can. I'm not going to go into lots of the functions that you can do on RDEs, because I think it's a bit boring, but you can look at the documentation, but just don't do group by. And repartition your data if you need to. And by that I just mean, in my original example, I had 4 blue blocks, 4 partitions. You can increase that number of partitions by a function called repartition, which will then, you can increase the number of partitions and a shuffle will take place. But by having very small partitions, you may get better performance, which is something to bear in mind. So what happens is, you will have some bad times when you're using PySpark, and people will come to you and they will say, why are you using Python? It's written in Scala, it's just not going to work on Python. I say, don't listen to those people, because when you actually talk to them in detail, you realize they're suffering from all the same problems that you are. It's just that to use Spark really effectively, you need to understand what's going on under the hood for very large data sets. So I'm going to talk, the graphic hasn't come out very well here, but I'm going to talk through an example of how you might implement a machine learning algorithm in Spark. I'm choosing a very simple example, which is naive Bayes. I know it's a slightly boring algorithm to go through, but it's quite simple, and I think it illustrates some of the design choices that you might want to make when you're making this kind of distributed system. So I'm just going to recap naive Bayes. This is a simple application of Bayes rule. You have a sequence of features, in this case, in our case, numbers, which are the x's, and a class, which is the c. So the probability of a particular class is equal to this thing on the right, which is the prior probability of being a member of the class, and then the likelihood, which is the probability of seeing your observations given conditional on the class being k, and then it's divided by this constant, which we won't go into. So here it's just represented as a proportion without the constant, and we'll implement it using the logs of the numbers so that we don't have problems with underflow. So this is how you do it in Spark. This is how this get tokens function just basically takes lots of documents and then represents them as a label. So this is supervised learning. So I have a label and then the token. So that's what this RDD looks like. Obviously, it'll be a lot bigger in reality. And then I kind of transform it a little bit using this map function to this new data structure, where I have each token, and then I have a list with 2 numbers in it. And those numbers represent whether that token is labeled true or false. So that's supposed to indicate the class membership. And what I'm really doing is I'm trying to create some counters so that I can count how many times the word dress, for instance, is found in the positive class compared to the negative class. And this is a slightly weird way of doing things, you might think. But in Python, you wouldn't do it like this. You'd kind of iterate over the original list and build up some data structure using some dicts or something like that. You can't do that in Spark because the data is distributed over the cluster, and you don't have a distributed dictionary that you can use. You have to build up your data structures in this kind of functional way using reduce. And that's what I do in this next step, this reduce by key. I simply apply this function, this lambda function, which is just going to apply, this is just a Python built-in map now. I'm just going to add all of the elements of X to all of the elements of Y in an element-wise way. So that means, and you do that for all of the contents, all of the values for each of the keys. So all I'm doing here is just adding up for the word dress, how many times it occurs in a positive class compared to a negative class. And in this case, 5 times it occurs in a document labeled positive, 15 times in a document labeled negative. Yeah. Then I'm not going to go through this. I'm just adding 1 basically to the elements of this list as a pseudo count, which is sometimes very useful in this kind of problem. A bit of smoothing. And then I get the total number of words in each class. And this is a kind of design pattern, I guess, that you'll see a lot. I just take a lambda, I take these elements, and then I just throw away this element there and make a new data structure, which is just true counts and false counts. So it starts off term, true counts, false counts, and it ends up just being true counts and false counts. I'm just throwing away the term, basically, in order that I can do another reduce and add up all of the numbers together to get the totals, because in the algorithm you need to know what the totals, how many words in total you got in the positive class, how many words in total you got in the negative class, in order that you can find the probability of a particular word in a particular class. Don't worry about the details, I know it's a bit hairy, but I just want to illustrate how simple it is in just a couple of lines to make this kind of distributed algorithm work. So this is something that's very important to understand about the way that Spark works. So you will be doing reduce by keys all the time in Spark. And it's important to understand how it actually works. So you can get by, if you're looking at data of around 60 gigs, you don't really need to know this kind of stuff. But if you're looking at very large data sets, unless you really understand this, you're going to crash quite a lot. So this is to illustrate what actually happens when you do something like reduce by key. What happens is a dictionary is created on each partition, on each machine that the partition is resident on. A Python process will do a reduce on the partition. All the examples I've had so far, the reduce by keys have been additions, so let's just say additions. I'm adding up these keys, K1 in this case. I add up the values for K1, which gives me 2 here, 3 there, and 5 there. And that's fine. That's just because that's just happening on the map side, on a single machine. It's not computationally intensive. Things won't crash. But what happens after that is that a shuffle takes place where all of the keys for all of the K1s are distributed to a specific reducer, in this case the first reducer. And when that happens, all of these keys are being shuffled all around the network. There are lots of files being created, memory starts to run out, and issues happen. So it's very important that you set the number of partitions correctly using this function. I'm aware that if you've never used Spark before, this probably doesn't mean much to you, but it's something that really matters when you're dealing with large data sets. But not only do you need to look at the number of partitions, you also need to look at the number of input partitions. So this non-partitions argument is very important, but it won't solve all of your problems. You also need to understand, you need to make sure that you don't have too many partitions actually as input to the reduce by key. for large data sets. So, that's a kind of naive implementation, and it works reasonably well. Using the reduce by key, but it is doing all of this network traffic, which is not very nice, and you want to try and avoid it as much as possible. So there's another way, there's another option for doing this kind of aggregation, and that's to use the aggregate function. So this is the API documentation. It says it aggregates the elements of each partition and then the results for all the partitions using a given combine function and a neutral zero value. So you basically need to create some kind of class which has a sec-op function and a comb-op function, and then aggregate will apply your functions to partitions and then apply the comb-op to all of the aggregation classes. I'll go through an example and make it clearer. So this is an example of an aggregator. You need to write your own aggregator, and all you need to do is have an add function and a merge function. And all the add function does is takes in a row of data from an RDD and adds it to this aggregating class. And in this case, everything is just being aggregated in this dictionary here called S. And all add does is take in a row of data and adds it to row S. I won't go through the code. The merge function takes in one of these aggregator objects and adds it to the original aggregator object. So you're just adding two aggregator objects together. The upshot of all of this is that you now have large objects which contain dictionaries with data in them, instead of having lots of rows of data which need to be distributed all over the network. Let's say you have 6,000 partitions. You now only have 6,000 objects to distribute over the cluster, rather than 4 billion rows of data being distributed all over the cluster. So it should, that should be quite nice. This is how you use it. I won't go over this in detail. You can look at the API documentation. And anyway, when I tried to implement this using a billion documents, it just didn't work and everything crashed. So don't use aggregate. And this is the reason why that is. These are supposed to be the partitions, these circles at the bottom. So aggregation will aggregate all of the members of a partition to create an aggregation object. So if there are 6,000 partitions, you'll end up with 6,000 aggregation objects. And it will then try and put them all onto the master node. There's only 4 there, but if there are 6,000, the master node is going to run out of memory because these are quite big objects. They may have, maybe a dictionary with 2 million words in it or something. So it doesn't work. But the designers of Spark have thought about this. And there's a new function in Spark called tree aggregate, which does exactly the same thing as aggregate, but does it over a tree structure. And all that means is that instead of just aggregating all of the partitions, or all of the elements of each partition separately, and then putting them all onto the master, it does it in an iterative manner, aggregating each partition separately first, and then aggregating a couple of partitions together, and then aggregating a couple of partitions more. And you can have tall trees, which means that the computation is spread out, and you don't get this horrible effect of lots of big aggregate objects being collected onto the master node. This is how you use it. And so I tested this on a billion short documents, say 10 words long. Using the reduce by key method took 18 minutes, and this tree aggregate method took about 10 minutes. But I have to be honest, and I had to hack away a little bit, and I had to modify the actual API of Spark to get this to work. And I put that in a gist. I won't go into details about what I had to do. It's actually just a very simple one-line change. But this is a new function. I think the concept is really interesting and something worth considering when you're implementing a new algorithm, but it's a new functionality, and you need to be a little bit careful. So I was going to talk about word2vec, but it seems like everyone's talked about word2vec to death. So I'm not going to go into loads of detail, but this is a nice illustration of how you can actually use this in practice. I'm not going to talk about this. People have talked about that. But word2vec is a really nice algorithm, right? And it works very nicely in a parallel setting. There is an implementation in Spark, and this is how you train it. I guess it's 4 lines of code. You can train your own word2vec vectors on a cluster on massive data sets, which is really, really nice. But then how do you use these vectors in practice? And people maybe haven't spoken about that too much. And I see there's 3 obvious ways of using these vectors. One is that you could just average vectors. You could take a sentence, convert it into vector form, and then just take average over it. You could do element-wise averaging over the vectors, which might work. I've tried it, and it didn't seem to work very well. Or you can cluster the vectors themselves to do some kind of dimensionality reduction, which I will talk about in a little bit of detail. Or you can use a convolutional neural network. But I'm not going to talk about that. I'm going to talk about how you can do this using Spark by clustering. So Spark has a very nice distributed k-means function, which you can use like this. I've just taken the pre-made word2vec vectors from Google here, and use k-means in MLlib to make 50,000 clusters. And it worked. I think it took like an hour or something like that, which is quite nice because this is 3 million words, 300 dimensions, 50,000 cluster sensors. It was quite a big job. I thought that was quite nice. So the idea here is that I'm trying to find which vectors are close to each other so that I can then use them to replace word features. So let's say you have a word feature which is shoe or lace, sole, things to do with footwear. This will hopefully replace all of those individual words with one cluster center, which will represent, footwear ship or something. The idea of being footwear, which is a dimensionality reduction technique, and potentially can help with things like classification problems. So how do you actually use this in practice? I've made my clusters. After making the clusters, I now need to send the clusters to, I was going to say send the clusters to the cluster. That's not very clear. These are my cluster sensors in a k-means sense, but I now want to send them to all of the nodes across my computational cluster. And I do that using this broadcast function. And all this does is it basically sends any variable you like across the whole of the cluster, and then it means that any map function that you then perform has access to that variable, which is really useful because it means you can do computation on the master node, make a big data structure, send it out to the cluster, and then all of the nodes on the cluster have access now to that variable. You can do some stuff. You can come back to the master node, update that data structure, and then send it back out to the cluster, and then some more computation can happen, which is very typical of the kinds of workflows that you see in machine learning. It's very useful. So now I'm going to talk a little bit about how to modify the naive Bayes algorithm that I just went over to do semi-supervised learning. So the naive Bayes algorithm that I gave you was a supervised algorithm. You have a bunch of labels and some data, and you want to build a classifier to classify documents according to the label. This semi-supervised method was published in 2006 by these guys, and it's a way of really, the algorithm just generates more training data, more labeled data based on unlabeled data. So you give it some labeled data as a seed set, and you give it a load of unlabeled data, and it will figure out a new set of labeled data by predicting labeled data from the unlabeled set, and then it will then use that to retrain itself. It's a concept called self-training. And for statisticians, this is an instance of the expectation maximization algorithm. But all you're really doing is in the E step, the first step, you just run naive Bayes on some labeled data, create the classifier, then do some prediction on all of your unlabeled data, and then treat your now labeled data as labeled data. So now you have a much bigger set of labeled data from your unlabeled data. Then the only slight wrinkle here is that you have to be able to predict the probability of class membership in order to do this. So you don't label things according to true or false. You don't label them in a binary manner. You label them with a probability of belonging to the positive class, which naive Bayes, as a generative classifier, is quite a sensible choice. So the only modification for the naive Bayes implementation that I gave is that instead of now using these ones and zeros as class membership, you have these probabilities. So you go through this step where you estimate what the probabilities of class membership are, and then you re-estimate again using the new labeled, this kind of artificially labeled training set, which is really cool. And this is why Spark is really useful in this kind of problem, because Spark enables you to keep your data set in memory. So for this kind of iterative process, we're looping over this, right? You might do this 100 times. Spark keeps all of your data in memory if you ask it to. So you don't have the Hadoop problem of writing all of your data out to disk, reading it back in again for every iteration. So for many machine learning algorithms, such as the expectation maximization algorithm, Spark is a very, very natural platform to use. Here's some results. So this is for 500,000 labeled examples. I have this precision recall and F1 score, and then by adding 10 million unlabeled examples and labeling them using the naive Bayes classifier and just doing 10 iterations in this case, I've increased the F1 by up to 0.14. It's labeled data for free. It's quite nice. And this is not interesting, but I did this on a very large data set. This is like 250 million training examples, and it didn't seem to help anything. And I think this is because if you have very, very many training examples, you don't need any. I mean, 240 million training examples is enough, right? You don't need any more than that. How are we doing for time? Okay, this is about configuration. Now, configuration I know is boring. You don't really need to listen to this. But if you do in the future decide to use PySpark and you have problems and things get bad and you feel a bit depressed, just remember that you saw this guy give this talk, go back to the slides and read the slides, because it will help you and make your life better. So this is how Spark works. You have your driver program, which is your master node, and then the cluster is distributed computations happening over the cluster, and you have many worker nodes. So that could be 20 or 40 worker nodes, and these are individual machines. Each one will typically have one executor, which is a process actually performing computation, and many tasks. You know, it's a multi-core machine. It could have as many tasks as it has cores, for instance. So what you won't find online very often is how you actually configure a PySpark cluster. There's loads of information online about how to configure a vanilla Spark cluster for Scala users, but for Python users, you really need to think about what you're doing, because each task is running in its own Python process. So you need to make sure that each Python process has enough memory. If you allocate too much memory to Spark, things won't work.
I'll stop in 5 minutes.
Yeah, sure. This is my last line, I think. So like I said, I'm not going to go into loads of detail. Come back to this if things start to break. The take-home message from this slide is that you need to make sure that there is enough memory for your Python processes to actually function. You can't give all of the memory of the machines to Spark, which is the obvious thing to do. If you follow the documentation literally, that's probably what you'd do. It's not a good idea. This is not a generic hiring slide. This is a real hiring slide. We are really hiring people for my team. So if you're interested in this kind of distributed machine learning on large data sets, come and talk to me or send me an email or something like that. Thank you, and I'll take questions.
I had a question.
You can shout.
Is it easy to set up start, get it started? And my second question goes to it is, if you've got a dead node, what happens? Do you, everything breaks or the system is robust?
No, it's robust to things like that. Sorry? Oh, the question was, is it easy to set up Spark? And then if a node breaks, does everything break or does things robust? So my team, we're an R&D team, so we don't necessarily make production systems. So if things break, no one really cares that much. But we use what's known as the Spark EC2 script, which comes with Spark. And it enables you to launch a Spark, like an EC2 cluster with Spark installed really, really easily. It's not super robust. I probably wouldn't use it in a production system, but if you're doing data science, R&D type stuff, then it's very easy and it works very well. The second question is Spark robust? It is robust. If a machine dies, everything just flows around it and computation gets re-performed when it's needed. And computation, I keep talking about this partition concept. The computation will only occur for those partitions which reside on that machine. That they will get rebuilt. Yeah.
Hi, I think you are using IPython notebook. Is that correct?
I personally am not. I use Emacs,
but your team
yeah.
And now I wanted to know your experience in that regard, limitations you have found. For example, can you use any kind of library in the nodes?
I'm really not the best person to talk to about IPython notebook. Sorry, I can connect you to people in my team who use it. So come and talk to me afterwards.
Okay.
I'll do that.
I think we should wrap up because we're going to start the lightning talks in just 3 minutes. So let's thank Martin.